Hi everybody, welcome to our exponential functions intro. We're going to explain these using our current status in the world of COVID-19. So our current real world model. We'll continue to use this data and these numbers throughout this lesson, as well as I will be coming to you in style with my brand new homemade face mask, just to be real festive. Okay, here we go. So let's look at COVID-19 today. As of this recording, but first, so something about exponential growth. Exponential growth can be a very desirable quality if it's modeling your money. It can be frightening when we are modeling a pandemic. All right, COVID-19 cases by day in the United States of America. This is starting January 22nd and ending yesterday, March 29th. These numbers come straight from the CDC. They report the numbers every day at 4 p.m., the total cases in the United States. So we are recording on 3:30. So these are numbers all the way from up to yesterday. So the question we have is, how do we model this kind of growth? You know, the functions that we know of so far, we know of linears, we know of polynomials, we know of square roots, and we know of rationals. None of those are really going to help us with this kind of growth that we're seeing. This growth, it starts off very slow, very, very, very slow. Right? It takes us to get to 10 cases. It takes us about 13 days to get us to 10 cases. And then the next, let's see, from 13 to when do we get to 100? And then the next 30 days, we get to 100. But then within 10 days we get to 1,000. Within another 10 days, roughly speaking, we get to 100,000. Okay? So growing rapidly. How do we model this kind of growth? If we want to look at the picture of this growth, let me move my pen out of the way. So if we want to look at the picture of this growth, here are the cases starting at the 22nd of January all the way up to yesterday. Yesterday, totaling about 140-ish cases, 140,000-ish cases. And notice the shape of this curve. These guys model exponential growth. So let's see what it is this exponential thing is that I'm talking about. So what we're going to learn, we're going to give a definition of what an exponential function is. We're going to give some examples of exponential functions, and we're going to look at a couple of their graphs. We're going to look at how to evaluate exponential functions. And then we're also going to look at the COVID-19 projection with exponential functions to see how these things are actually used in real life. I have an equation that I came up with, as well as a projection of what's going to happen in the future if nothing changes. That'll be at the end of the video. So, definition of exponential functions. An exponential function is the function in the form of, switch my pen, in the form of this. F of x equals c times a to the x power. Think of c as just a number. It's a constant. A is also just a number. Okay, but the stipulation on a is it has to be greater than 0, and it cannot be 1. These are really important. The stipulation on c, it can be anything, but it can't be 0. Okay, so the domain of the exponential function is all real numbers, so we go from negative infinity to infinity on the domain, and the range will vary according to the values of c and a. So the value of a is also known as the base of the exponential function. Basically, a has to be greater than 0, a can't be 1, c can't be 0, and your variable shows up in the exponent. That's the main reason why we call these exponential functions. So something that we can have would be like 2 times 3 to the x power. Something that we cannot have would be 2 times negative 3 to the x power, right? Because that would be an a less than 0. That's a no good. This is good. This is not. Okay, so let's see some other examples. So here's some other examples of exponential functions. So here's your c, here's your base, here's c here, here's a base here. C in this case is 3, the base is 2/3. The c in this case is also 3, the base is also 2/3. Notice the variables are in the exponent. Again, that's the main point here. Is your variable is your exponent. And then A has to be greater than 0. C just cannot actually be 0. A also cannot equal 1, which all of these satisfy. So we're all good on that. Let's see what these graphs look like. So let me move my pen again. Come on, pen. Let's go over here. So the blue line was our first equation, 0.5 times 2 to the x. And notice this is exponential growth. This kind of looks like the COVID cases. It starts off really slow and it takes off. Our green line is very similar. The only difference here is that our variable is negative. Okay, same C, same A, negative variable. Oh, look, it's exponential decay. I wonder what could be going on there. We may see that in a future video. Our black line, our variable is also negative, so we would expect to see the same exponential decay. However, our A is also a fraction, so our A is greater than 0 and less than 1. What does this all do? Well, look at our black line here. Oh, that's interesting. That's also growth. Something weird going on there as well. Again, future video, we may figure that out. Okay, then the red line here, the variable is positive and it's a 2x. And our A is also, again, between 0 and 1. It's a fraction, it's 2/3. So what does this do? And the red line looks like, oh, that's also exponentially decaying. There must be some kind of pattern. I wonder what it could be. Well, future video, I'm sure we'll discuss exactly what that is. But just know, graphs of exponents, they display exponential growth or they display exponential decay. That's all we need to know for now. How do we evaluate exponential functions? Well, you evaluate an exponential the same way you evaluate any function. Plug the number in for x or for t or for k or for your variable or whatever it is. Just plug it in. So before we start, which one of these do you think is the biggest at 2, and which one of these do you think is the smallest at 2? If you look at your C's, your A's, whether they're negative or positive variables, I don't know. Maybe again in a future video we'll be able to predict this, but for now let's just kind of plug it and play. So f of 2, in this case here, this would be 0.5 times 2 to the second power. This is going to give us the number 2. 2 squared is 4. Half of 4 is 2, so that would make sense. What happens when we plug into here when we have the negative x? Let's see. Well, f of 2 in this case, 0.5 times 2 to the negative 2 power. What does this do to our function? Oh, this gives us 0.125. This is significantly smaller than that, but still greater than 0. They're both positive. Okay, interesting. What happens when we plug into this function? Let's see, 3 times 2/3 to the negative 2 power. Well, what happens here? We plug this into the calculator, we get 6.75. Interesting. That's a negative. That's a fraction. And this is much bigger than this one. I wonder how that happened. Plug in 2 to our last function. 3 times 2/3 times 2 times 2 up here. And we get the number, and I'm going to simplify this, I'm going to round off a lot. We get 0.6. So, this function here was our largest when we plugged in 2, and this function here was our smallest. But notice when we plugged in 2 each time, we still got a number greater than 0. Interesting. We'll see again in a future video. We'll look at all these properties and see exactly why this happened. Okay, but now for the question of the lesson. If nothing changes currently, how many cumulative cases of COVID-19 will there be in the USA by Cinco de Mayo? There's a lot of variables here at play. This is real life, so exponentials, these mathematical models can only do so much. I'm going to preface this with saying this is not like for certain per se. However, this is just what the numbers tell us. Okay. So in a future video, I'll show you guys how to come up with equations that model exponential growth. I did kind of all of this before the video, but if we look, the number of days from January 22nd to Cinco de Mayo, or 5/5, was 104. The exponential function used to model the COVID-19 growth, this is something that I figured out based off of day 68 from the CDC and the data there, is e to the 0.17t. E is these are exponentials, right? T is the variable is in the exponent. We'll talk about this number e in a future video. It'll actually be in the next video. Just for now, take it this is the exponential function. So we're going to evaluate this exponential function for t equaling 104, and what do we get? Again, this is to say nothing has changed, okay? Everything is going exactly the way it's going. Nothing has intervened. Nothing has happened. How many cases will we have come Cinco de Mayo? 47,678,923 cumulative cases. So this is from January 22nd to May 5th. If nothing changes. Now this is the cumulative amount of cases. This is not saying this many people are going to be currently sick at one time. It is saying that if we totaled up every single case that has been reported and confirmed in the United States from the 22nd of January to May 5th, okay, again, this is a very simple mathematical model. There's way more variables at play here than I've put into my equation, but this could potentially be our number by then, if nothing changes. That's why it's so important to try to make a change. To flatten this curve is what everybody says. Here's the graph. Okay, days are on the x-axis. So this is days. Day 0 is January 22nd. Okay, day 80. We are in day 68 right now, so we're somewhere around here. Day 104 is somewhere around here. Okay. These are huge numbers. This number here is 20 million. This number here is 40 million. 1, 2, 3, 1, 2, 3. This number here, 60 million. So you can see how quickly that we can get from 0 to some number like up to 60 million. Okay, so exponential growth. It is huge. So here's the graph. Alright, so to recap, exponentials are the fastest growing / decaying function we've seen thus far. Exponential functions have the variable as the exponent, right? They're like an a to the x, c a to the x. The stipulation on a is a has to be greater than 0, a cannot be 1, and we just need c also to not equal 0, okay? Otherwise, kind of anything else goes. And as we've seen in our real-world example, exponentials model real-world examples such as disease. They model compound interest, the way bacteria grow, lots and lots of stuff. So I hope that was informative. If you guys have any questions, please, please, please don't hesitate to ask, especially if you want to know where I got that exponential formula for the COVID-19 cases projected. I'd be happy to share. Otherwise, I'll see you.